Good morning, everyone, and welcome to this first Meet the Experts session from TNO. Today we are talking about what's new in safety assessment for automated driving. My name is Joke Welte and today I'm your moderator. So before we start, please turn off your microphone and your camera. If you have any questions, we don't use the chat today, but we have a Q&A. So please use the Q&A for all your questions or your remarks. In the end of this session, we have 10 minutes left to answer as much questions as possible. And also later on, we will answer more questions. So what's the program of today? We will start with my colleague Henk Goossens, one of the TNO experts who will talk about why are we here today. After that 10 minutes, we will have Olaf Optenkamp and our guest Michael Jung-Oost from Volvo, who will talk about the concepts for concepts of safety for automated driving. And by the end, we have 10 minutes left for a Q&A session. So, Henk, let's start with you on why are we here today?
Thank you, Joke. Yeah, that's something I will try to explain. And in my role as a partnership manager at TNO, I talk with a lot of people in the industry and I try to follow the trends. And something that is becoming clear to me is, and I have to switch, of course, to the next page. Yeah, now it works. Is this question, so are we really at the last hurdle of automated driving? I think we're all familiar with the early experiments in the 80s and the 90s of Mercedes-Benz. And since then, a lot happened. So sensors have become a lot better. Compute power has been increasingly abundant. And we have learned a lot about AI. Now, recently, there's also regulation in place at European level and in some countries. So the question is that really the last hurdle we have to take, the safety assurance? Because we are seeing that vehicles can do a lot of tricks. We see that in videos, but the question is, can we have the confidence that they always do the right trick? And that is, yes, not the case, unfortunately. So this one made it to television in the US. This vehicle was swerving a lot. And so it appeared actually on television. And there are quite a few more cases in this cloud of potential or real safety issues. The question is, do we now have a swerving gate? Should this vehicle be prohibited on the roads because it's really not safe? I think that is really the question. And so we have to ask ourselves, what do we conclude from one such a video? Either a bad video showing not such a great behavior or good behavior. And the answer for me is actually nothing. We cannot judge, we cannot say anything by one video. I think we need much more better safety evidence that's quantifiable and that's also understandable. And that's a complex thing to do. Obviously, variations in the real world are many. The systems that we develop are very, very complex. And then in some vehicles, there's even a driver, a human. And we know that humans are unique and can have very specific behavior. So what we have to do for this difficult problem, we have to break it in pieces, I think. There's no simple one-size-fits-all solution for every aspect of the safety assurance. We need to break it down into safety risks. What is actually causing the safety risk? And then understanding the mechanism behind it, understanding the probability and the severity, judging whether it's really a safety risk or another risk. How can we mitigate it? And then last but not least, how confident are we about all of these assumptions and judgments on safety? That is what we have to do per source of risk. And for every source of risk, the methodology might be different. So that is quite a lot of work. But there is another problem as well. And that's what we see as well. This technical issue, technical challenge immediately translates into a communication challenge. because inside the automated vehicle company, there's a lot of collaboration going on between the safety engineers, so the engineers, and, for example, simulation, data analytics, and also the management. And for them to speak the same language is not always obvious. And also, there is this question of transparency. So safety has to be communicated outside the automated vehicle company, with policymakers, with general public, with consumer organizations, with insurance companies. We'll see that also later today. And also their communication is not obvious. Sometimes it even feels chaotic. And that's actually why we decided to have this webinar, this series of webinars. So why we are here, to help create a common language between those that are very deeply in safety assurance and those who are not. And on top of that, we hope to share with you a few solutions that we think are the right direction for this complex problem. So with this, I'm happy to give it over to my colleague Olaf, who's ready to share with you the main concepts of safety insurance.
Thank you, Henk. Almost there.
Thank you very much, Henk. See if I can. Yeah.
So we will start now with my colleague and TNO expert Olaf Optenkamp. He is senior consultant and he will talk about concepts of safety for automated driving.
Yeah, thank you, Jochen. Actually, I just returned from the JSAE conference in Japan, where I gave 2 presentations on scenario-based safety assessment for an application on an airport and an application on the public road. And I realized that by doing that, we very much tend to dive immediately into solutions. In this case, the use of scenarios for safety assessment of automated driving systems. What I would like to do today in this webinar is share with you some of the considerations why we think at TNO that scenario-based safety assessment is a good approach. But even before doing that, I would like to take one step back, because we already used the word safety a lot. It's also good to just think, what do we consider as safety? If we look at up on the Wikipedia page, then it's the absence of accidents and incidents, or coming to an acceptable level of risk. I think that is quite clear and understandable by all. Actually, in 2015, Professor Holnagel distinguished 2 types of safety: safety 1 and safety 2. And for safety 1, he says, well, actually, I define safety as a state where as few things as possible go wrong. So we assume that things go wrong. We identify the failures, why things go wrong, and take that into consideration in the development of specific components for safety. And that has been the approach for a very long time. So if we look to, let's say, the traditional approach, we count accidents, casualties in traffic, fatalities in traffic, unfortunately, and we identify the causes why these accidents happen. And we also perform a risk assessment to determine the likelihood of the causes to occur, in order to develop systems to prevent these things to occur in the future. And based on that, we also define policies, for instance, in the EC, that we say, okay, we want to move to 0 fatalities in traffic by 2050. And by looking to the current causes for accidents, we try to mitigate these causes to achieve this type of goal. Taking a step back again, looking to, let's say, all the developments maybe since 2010, then we were really looking towards a transition from passive safety, in the order that we develop systems to mitigate the consequences of a crash towards active and integrated safety. So trying to find systems in the vehicle to avoid a crash, or at least make sure that if the crash is imminent, that we mitigate the crash itself. And then we still have the passive safety systems to mitigate the consequences of that crash. And we very much used the graph that I showed here, where we look to the different type of systems given the time to collision that is used as a kind of metric for the criticality of a situation. Time to collision is, let's say, roughly indicated by the distance between two vehicles and the relative divided by the relative speed. And during normal driving, this time to collision is close to infinity, let's say. But if we deviate, if we move more towards a critical situation where time to collision, let's say, goes beyond below, let's say, 3 or 2 seconds, we developed systems to warn the driver to return to this normal driving situation. Well, not always that is possible. It is possible that the time to collision further decreases. So we develop systems to try to avoid the collision. So AEB systems are a typical way of engaging in this time sequence. It is possible that still the criticality increases, and there is a point of no return that we know, okay, now we are going into a crash. Then the only thing we can do is try to mitigate the collision. So in that case, brake forcefully in order to get as much energy out of the system before the crash actually happens. And if the crash happens at time to collision is 0, then the injury mitigation systems come in place, and there is also post-crash systems. So all type of systems that have been developed, and they follow this sequence of increased criticality in order to try to move the system and also to try to move the driver towards normal driving. You could say that is a kind of operational safety. You might call it tactical safety. There can be a lot of debate on the proper words, but that was, let's say, things that have been developed in the last 2 decades. Then things, because of this increased automation in vehicles, it became possible to further automate the systems. And in 2016, the levels of automation have been introduced by SAE in J3016, and many different systems have been developed since. It's advanced driver assistance systems, of course, originating from these active safety systems, which would be called a level 2 system, where the system assists the driver during its complete driving task. There are also level 3 and level 4 systems already available. Examples thereof are advanced lane keep assist systems. And there are even level 4 systems like shuttles or automated valet parking that take over the driving task from the driver fully when being engaged. And now lately also other developments took place. We go a little bit back in terms of a level to a level 2 system for a driver control assistance system. You could consider that as an example, an hands-free highway pilot. And there the system supports the human driver during the full driving task. All these type of automated system bring us to a new era of safety. And that's where the second safety principle of Hollnagel appears, is safety 2, which relates to the system ability to succeed under varying conditions. So what we try to ensure is that during the complete driving supported by the system, as many things as possible go right. And the safety 2 approach assumes that everyday performance variability provides the adaptations that are needed to respond to these varying conditions, and that we are trying to do things as much as possible right. So in my view, safety 2 really comes more towards the automated driving than the original safety 1. What is then safe automated driving? Yeah, you could say it is something like driving normally without any incidents. You could also say it's driving as a competent and careful driver, or a very attentive driver. We also call that safe and social driving, anticipating very well to all the variations that we encounter, and show predictable and acceptable behavior on the road. Now, more on these human references for safe and social driving, you will also see during our Meet the Expert session on June 27th. Besides, let's say, behaving well on the road, the regulation, of course, also indicates to us that we should avoid any reasonably foreseeable and reasonably preventable crashes under the large variations of scenarios and conditions that the system can encounter during its operation. Now, safe automated driving requires that we, of course, consider the safety standards. And I mentioned only 2 of them. There are many more. We will also discuss these on June 13th. As the first one, the functional safety standard 26262, which indicates that we need to respond appropriately in case of failing of components on board. And the second one, safety of the intended functionality 21448, to prevent and mitigate hazardous events that are caused by functional insufficiencies or unexpected conditions. And both these standards are very much related to this safety 1 principle. Have we developed the system well? For automated driving, we also need to consider this safety 2 perspective. Have we developed actually the right system? And that brings me to Mikael, to you, to see how you at Volvo Car deal with this.
Yes, thank you, Olaf, and welcome, Mikael.
Well, thank you. Interesting stuff, and it's good to see a lot of people online listening. Apparently AD is not dead yet, so that's cool. I'm Michael Jung-Aust. I work for Volvo Cars at the Safety Center. I have been doing a fair bit of thinking on what we need to do in order to convince people our autonomous driving functions are safe when we release them. So I'll talk a bit about that, and I'll also, to keep you kind of interested toward the end, and do a little thinking of your own, I ask you to think about what is the best sports metaphor that we can come up with in doing this work. Now, I think one thing we should start with, perhaps most people already know this, but it's essential, I think, I'll say it anyway. Why can't we just drive a lot to prove that our function is safe? This question comes back from time to time, so I better get it out of the way, I think, before I say something else. And I think the intention is good. Like, you take your product, you show that it works in real life and that it's safe, and that's your approval before you deploy it to the wider public. Problem here is we're dealing with something that has implications. So if we wanted to prove that, for example, a self-driving vehicle had half the chance of fatal crashes compared to normal driving, Then we would look up, how many miles do you need to drive in, for example, Sweden, to be involved in a fatal crash, statistically speaking. And then we would send our cars out on maybe twice that mileage. So we would be expecting 2 fatal crashes. And then when all that driving is done, and if we only killed 1 person in the process, we would be able to argue that, this is twice as safe as normal driving. The problem is killing that 1 person in the process. That's completely unacceptable for so many reasons. And imagine that more car developers than just Volvo were striving for autonomous drive. Then everyone would be sending a lot of cars out to do a lot of driving, putting out a lot of emissions, killing a lot of people in order to prove that their cars are safe. So that's not really a viable option. Which means we have to find other ways to discuss safety of these cars. So any safety argumentation, and this is the important bit, it's always going to be a prediction. Some empirical data can be used as a basis, but we can't collect the type of data that leads to more traffic problems. So we'll have to base it on data that's safe to collect, so to speak. And that's the challenge. So I'll be moving forward here. Let's see if that happens. So when we are to develop and sell a self-driving car, we have to show it is safe at least 3 times. The first time is before we start selling it, when you have all the hardware inside. But as you might be aware or should be aware, that most who are trying for this, they are not enabling self-driving right away. First, they do a lot of data collection, and then they try out the function in the background. What would the algorithm do given this sensor input? And then after some time, when you think everything's fine, that's when you actually enable your self-driving function. That's step number 2. And lo and behold, all is well. The cars are out driving. And then inevitably, because statistics are statistics, one of these cars will get involved in a crash. And then there will be a discussion on, whose fault is it? Was that proper behavior or not? What do we do? What do we learn? Etc. And at all these 3 time points, we have several different audiences. We have the public or media. We have the government and the regulators who want to understand whether they should allow us out. We have the insurance companies, if they are not sure that the cars will not lead to a lot of damages, they won't let them out. If the insurance companies thinks that, settling an AD case insurance-wise, if that's going to take 3 days, and today settling a manual driving case takes 10 minutes, they will want to raise the premiums accordingly to get paid for all the hard work. And perhaps the most difficult one, actually, is for our case at VCC, Volvo Cars, the internal stakeholders, the people involved in developing the functions. They might sometimes be the hardest to convince that we should enable this. So we need argumentation that can convince all these different audiences at all these different time points. And I'll outline our thinking of how we want to approach that, so to speak, today. So it's big strokes with big brush. Don't expect detailed answers, but I'll talk about the big strokes, and then we can ask, is this a good way to do it? I had to include this example because there is, of course, other ways of doing it than what we propose, and this is a fantastic poetry option that comes out of a real safety report from a real company trying to do autonomous drive. And here the safety argumentation is based on a symphony of signals that are providing different but complementary notes and harmonizing with field data. So this is a very musical, symphonic, and poetic version. If you were asking yourself, is AD safe, and you were faced with this statement, chances are you would give credit to the author for the formulation, perhaps not understand a whole lot more about whether it's safe or not. So we won't do that. We're a little more like hardcore, perhaps. So what we think, bottom line, that we do need to show before cars go out and even after they crash, if they do, is that, for one, a self-driving car should not repeat known types of mistakes that lead to crashes. In other words, the type of problems that people have today, the causes why people crash in traffic today. There is no excuse for not being able to deal with those. They are known. You can handle them. You should be able to. Then the second category is new problems. So one thing that seems to be a fear among people is that if we put a robot behind the driving or steering wheel, what guarantees are there that the robot doesn't make new mistakes that humans couldn't because they aren't wired that way, but which robots might because they are robots? So we need a good argumentation in both these areas. Like, first, we're not repeating human mistakes, and two, we're not creating new robot mistakes. So let me start out with the first one, which is the human mistakes. One thing you cannot really ask for is perfection. Every technical system has, the potential to fail at some point. So in this comparison with human drivers, we need to find a reference point or a bar, so to speak, where the standard is high, but not so high it's not possible for mistakes to occur, because that would be impossible. One way to define that reference point or the reference model is to use statistics and say that, on average over this many miles, this type of error shouldn't happen more than this often. The problem is, even if those statistics are correct, statistics on that level really don't make much sense to most people. If you're talking to journalists, or if you're talking to especially everyone not an expert in statistics, basically, even if you have, a very nice statistical model and you have the variability of your 1,000 control parameters well described and can show their containment within safety boundaries, to most people, that's just a long list of Excel stuff with incomprehensible data. It really doesn't tell you whether it's safe or not more than the poetry option did. So we need another approach. And here we want to work it out along the lines of a very basic concept, which says that you shouldn't make human errors if you're a self-driving AD vehicle, and crashes happen when people have a bad day. You miss something, you're slightly inattentive, something weird happens. So if we look at all those situations where you had a bad day as a human, what would be the outcome if you'd had a good day? And when we know that outcome, then that's the bar to strive for. What would happen if all humans had a good day instead of a bad day in the crashes that occur today? And when we know where that bar lies, let's make sure our autonomous vehicle is just a little better than that. Because then we can say what I've written to the right, the left, down to the left, that if there is a crash, it's extremely unfortunate, but we know for a fact that no human driver could have resolved this any better. Emphasis on human, mistakes are possible, but we've put the bar for performance on the level of someone having a really good day, doing their best in traffic. And people who are in that position, they actually crash very rarely. People are pretty good at driving. If you look at statistics, it's really volume that creates a traffic safety problem in that sense. But anyway, this is the high level brush stroke. Let's put a reference model in place with performance where people can agree, if that person drives in traffic, I would, like to have that person as a traffic companion. That's a good driver, and make sure our AD vehicles meet that standard. Done? No, not super simple, but that's the goal. And then we have this type of examples that come up if you want to like understand how this plays out in reality. So here we have a situation. There's a car coming. There's someone running into the street. Obviously, the car can't see the person because there's a truck in between them. And here you would ask yourself, what would an attentive, well-behaved human do? Well, first off, maybe you would slow down a little because you know you can't see through the truck. And because you're an experienced person, you know people may walk into the street. So here, maybe you would drive a little slower. And if you're driving a little slower and this person comes running out, what are the advantages of being autonomous? Well, you're faster. You have a reaction time that's a little faster than a good behaved human. And then you can do conceptual example like this one where you say that, so in this case, and this case is actually based on a real crash that happened where the pedestrian died. The blue line here on top, it's what happened in the original case. The driver was doing 70 kph. There was no reaction before the crash. Now, if we have this like attentive person having a good day, we think first off, well, the good things to do is to slow your speed down a little bit. Here we put it at 30. That's probably overdoing it. You have to find a good balance between actually going forward and being precautionary, safe. But we slow down, and when we get to this point where the actual pedestrian is visible, you can see that with the 0.2 second of reaction time you can have in an autonomous vehicle versus the 0.6 of a fast driver, but 0.6 is being pretty quick on the brake if you're human. The AD vehicle will actually stop even a little earlier than the attentive, good human driver would. So this is the idea. If you work through existing crashes, typical crashes, that is, not the weird ones that we can never get to or the one-offs, but the ones that we think are based on scenarios that will keep on happening in the areas where we are driving, then you can work out what's performance levels that should be, set as targets for your autonomous vehicle. And that saves us from, requiring an infinitely fast autonomous car that's infinitely precautious. The only realistic implementation of that is a car without an engine that can't move. As soon as you're on the move, uncertainty occurs. And this is very conceptual. You can think of a million problems in this once you look at it. I can assure you, others who looked at it have thought of a million problems with this, and we're trying to work them through. But we think you need some reference of this type to really come to this point where you can say that our function is just as good as or even a little better than really good human drivers. And if we don't agree that's the goal for an autonomous vehicle, then let's have that discussion rather than fight over the details of this model. Right, so that was for avoiding repetition of current crashes involving humans making mistakes. And then we have oh yeah, I had an slide till, sorry. We'll stay with this one more slide. So if you take this reference model and zoom out a little bit and ask yourself, what are we trying to achieve? Then I think the first bullet here really sums it up. It's computers, so they calculate in time steps. They are fast, but it's still, time steps. But in every time step, you have to ask yourself, if you're out driving this autonomous car, is it safe to continue? Or should you stop? That's the basic question. And it needs to be answered at all times with a high repetition frequency. And the decision should, of course, be based on, what objects might pop out, what's our ability to detect them, or if you turn that around, what's our ability to show that the lane is actually empty? Maybe you don't need to detect stuff. Maybe it's enough to know that actually tarmac ahead, open, no problem. And what is the outcome? Should we hit any of those objects that might come into our path? Because if it's trash bag, no problem. It's if the person, big problem. And the goal then is to be normal and safe. Normal in the sense that we want the car to be predictable. If we deviate too much from how people ordinarily drive, we are actually by definition creating an unpredictable car. That's not doing what others do, and that makes it unexpected, and that makes people both make mistakes or misinterpret and do other bad things. But even in normality, or perhaps by definition normality, there's a certain variability to it. So you can always err on the safe side of normality without becoming unpredictable. And I think that's the goal here. Let's be like everyone else, but a little safer. So to me, this is a perfect match to, I think, how almost every human driver think of themselves in traffics. I'm just a little better than everyone else, even though I'm mostly like everyone else, but I'm just a little better. And we would like to create that for real. We'll see how it goes. But even if we go through all these problems that people have experienced and make sure we can handle those, there is other stuff that can go wrong with a robot. So even if the autonomous drive, you can't really distract it, you can't get it drunk, it can make other types of mistakes before, maybe mistaking a green light for a red one or something else that has to do with perception processing. If you give people a few minutes, they will give you a very long list of possible robot mistakes. And if you give it the task to engineers, they will give you an infinitely longer one in a shorter period of time. They're very creative in this domain. So the second part of the problem is really, how do we handle that? And here, thankfully, the problem of autonomous drive is not unique. It's the same problem as when developing any technological product with a potential safety implication should it malfunction during operation. And to handle that, the engineering community has developed a bunch of standards saying that if you are to deploy this tech, your performance needs to be good. And one way to ensure that is to follow standards for what is good performance. So we actually think that if you really want to avoid a system that freaks out and does weird things, applying the safety standards that are in place for tech systems to keep them from freaking out and doing weird things is the right way to go. These are established standards. Smart people have helped made them. It's very quantifiable. You can measure stuff. You can do numbers. It's super techy and nerdy for those so inclined. And it's really there to prove that technologically speaking, your function is at a state-of-the-art level with no known flaws of technological character. So we think this robot error problem, standards are the way to make that go away. The only thing you leave behind then is, what happens if you're making a new type of mistake that wasn't predicted by the standards or by someone else? And to that, I guess the only thing we can say, well, that's possible, and let's deal with that when the time comes, and let's make sure we have some kind of monitoring systems in place so we can actually see deviations that might predict this weird error. But it's really asking a lot to be able to predict the future with total clarity. Most people can't do that. So I think this is, if we're happy with standards that are meant to give us safe bridges and safe roads, we should be happy with standards that are meant to give us safe cars. That's a reasonable level of comparison, I think. So that's that. And now we come to the sport section of this presentation. But first, to recap a little bit. So what I've been saying is essentially, before we launch a vehicle, we can't drive enough to show it's safe, because that would involve literally killing people to prove ourselves safe. Stupid idea. But we need to show we're not repeating human errors. And here we think we need a reference driver model where we can say that the performance of the car should be as good as a really good human driver. And we can figure what that level of performance is out, and then we can design toward that. And then we can say, our driver is as good as any good human driver, so no one else could have done this any better. And then we have the robot errors, weird stuff happening in technology. Here we're saying that if we should go this route, fulfilling all the standards is a good way to show that our technology meets current state-of-the-art levels of performance. And again, no other engineering team could have done this any better. It must be possible to fail and having done your best, and not being completely shot out of the water. Otherwise, new technology would never develop. I think it's the way society works, basically. Now, with this too, and if you remember the long list from the start with all the audiences and all the different time points, I would like to say that if you want to go live with an autonomous driving system, an ADS, it is a bit like qualifying for a decathlon in the Olympic League. And, a decathlon, it typically has 10 sports things you need to do. You have 4 runs, you have 3 jumps, you have 3 throws. You don't need to be the world champion in any of them, but you need to be good enough in all of them to qualify for the Olympics. There is no entrance into decathlon unless you're really Olympic level good in all these 10 different sports. And we must qualify not just in one type of decathlon, but 2. We have both the human error version and we have the robot error version. So getting a good safety argumentation in place at the right time to the right people with the right content is a bit like being an Olympic level athlete in 20 different types of sport at the same time, and trying to keep a really cheery smile on your face while doing that, because no one likes a grumpy presenter. And I think that concludes my talk for today. And if you have other sports metaphors, please drop them in the Q&A channel. I need, more inspiration, and any suggestions you have are welcome. So with that, back to you.
Yes, thank you, Mikael. And also for all your other questions, not sport related, please put them in the chat.
In the Q&A chat.
In the Q&A chat, indeed. Olaf, I will give the floor again to you. Thank you, Mikael. Then we come to our conclusions for today before we start the Q&A session.
Yes, let me see if I do get control of the system. Yes. Yeah, I really would like to come to a kind of conclusion for today in how do we determine that we designed the right AD system. Mikael indicated we need to show proper behavior in those situations that might occur in the future, based on what we have experienced so far. And we need to get an understanding of what is proper. So what is the bar that we measure that against? And how do we show that then in the end to all the various stakeholders here? So let me. So putting safety assessment together with this safety to perspective. The safety to perspective relates to succeeding under these many varying conditions. And we use scenarios usually to describe these large this large variety of situations and conditions in a way that we try in a structured way to give such descriptions and to also make that measurable. So in the end, it's not that we need to have a quantified way of drawing our conclusions, because that is the way that we can communicate these conclusions. And that is the reason that we use scenarios to first try to describe the operational design domain of our system. So what are actually these situations and variations that we might expect that occur during the complete operation of our system during the lifetime of the system. So indeed, we try in a way to predict the future based on what we have experienced so far. So scenario-based safety assessment is used to evaluate the system's ability to respond then properly or appropriately to each of these possible situations. And that's also what is reflected in the new assessment test method for automated driving from the work program 29 of UNECE, where a scenario-based multi-pillar approach is proposed, where scenarios form that key element to quantify and structure all these driving behaviors. Now, that is just a scheme. So what we also try to do is operationalize that. So how do we do that? And I just put up here a list which is not complete, but what we do is we need tools for those for identifying and characterizing those scenarios. We store them in a scenario database for having these quantifiable measures, and we use scenario statistics for that. By doing that in that structured way, we are capable of identifying whether the scenarios that are in our database give a complete view for a certain selected operational design domain. Based on those scenarios, we need to be able to generate test scenarios for the different ways of testing, whether we use simulation or testing on a proving ground or even on the road. And based on those results, we need to be capable of building a safety argumentation using also reference for safe and social driving. So taking the bar that we need to consider, and as clearly explained by Mikael. And that brings me to the conclusion. I would like to take the opportunity to invite you to read our position paper on Streetwise, the scenario approach of TNO. We had a first position paper in 2018 that really needed an update. That update is ready. You will find the basics, the implementation, and the future of scenario-based safety assessment in that document. And I drafted here the link from which you can download that. And with that, I would like to hand over to Yoko for the Q&A session.
Yes, thank you, Olaf. So if you have any more questions, please put them in the chat. And I will start with the first one. The driving conditions and road users constantly evolve. Think, for example, for the growing number of dynamic electrical steps. I think this question is for you, Mikael. What's your opinion about the continuous improvement requirements for AD systems as outlined in the UL 4600 standard, using safety performance indicators after AD system deployment? What is your opinion on that, and how do you deal with that?
Well, first off, I don't know the standard as such in detail, so I can't answer for how the standard works with that. But I would say that you need a system design that's resilient toward new things. So if you're a teacher and you have a way of teaching and some new student gets into your class and asks different questions or behave differently than your previous students, I would say you're not a really good teacher if you're like completely stumped and have to stop the class because you don't understand this weird thing that just walked in. In the same sense here, and this is, I think, why this question, is it safe to keep on driving, is really at the heart of it. All the scenario generation we can do is always retrospective. It's things we know or can think of. So it's always going to be one step behind the new and unexpected. So your driving principles and the answer to the question, is it safe to continue driving, cannot depend on being able to identify a particular scenario beforehand or have thought of it beforehand. You need more robust principles than that. And in our case, it's very much a kinematical, physical kind of safety problem. So you need to be really sure that your cameras and radars and other lidars and sensors can actually detect objects. And if they do, you need to have a good policy in place for how to handle any object detection. If that is general enough, then it really doesn't matter what stumbles into view. You have a principle for dealing with it. And also, we are working a lot on complementary principles, like a completely independent way of using the sensors is to look for, it has different names, but one word is drivable area. So how much space in front of the vehicle is unoccupied and is consisting of flat tarmac. We don't want to go over edges. But so you have a definition of drivable area. And of course, if that area is big enough or good enough, then you have another mechanism that ensures you can handle new things. Because if that gets occupied by whatever, you can deal with it. So in this case, then, I have a good friend at Chalmers University. Some years back, he's a lot into micromobility, and some years back, they purchased basically every type of one or two wheeler that they could lay their hands on that people use in traffic, these electrical stuff, to understand, how they drive and how you can do slalom and how you can pop out into traffic. And I think they learned to ride most of that. Some were completely unrideable unless you were like these mono wheels. They are, only for the very gifted.
Yes.
in balance. But the outcome of someone on a new micromobility device popping into the lane of an oncoming autonomous car, that outcome should not depend on us being able to identify, like, is that a mono wheel or is it a regular scooter, or is this someone sitting on a mono wheel with a support pillar? Doesn't matter. It should be robust against that. So I think the short answer is you have to design for the unpredicted.
Yes.
And the trade-off to authorities is basically, how much mobility do you want? Because if we're going at 3 kilometers an hour, we can stop for anything at all times. If we're doing 30, still stop for anything at any times. Once you go above 60 or 70, you are starting to take a little bit of a risk, because you cannot really stop on a dime in the way you can at lower speeds. So I think that's you have to expect the unexpected and have a principle for it. Otherwise, you're not really fit to deploy ADS.
Thank you, Mikael. Then I go to the next question. I think this one is for you, Olaf. Can you give one or a few examples of the scenario-based safety assessment? And do you think it's possible to also come up with some specifics for the safety requirements in these scenarios?
Yeah, that's a good one. One example where we really applied scenario-based assessment up till the moment of introduction was at Changi Airport in Singapore, where we made an investigation. What are the typical variations and situations that baggage tractors need to operate in environment of the airport. In one way, it's a very difficult environment because of the strict regulations that you have on not being able to. Nothing may go wrong in the operation, but also it's a difficult environment because of the many different type of vehicles and road users that you have there. On the other hand, it's rather structured because the routes are quite fixed. And there we really went from collecting information to come to this scenario overview, determine what are the variations within each of these scenarios, and also determine together with the operators at the airport what is the acceptable behavior that we would like to see, where vehicle developers made use of these tests and showed in simulations based on these test scenarios how they would go into each of these variations. That's just the practical application. It is in the V for Safety project, for instance, where we show what are the different possibilities of performance of safety solutions. And also there we use a scenario-based approach where we try to get a feeling on what are all the situations that the vehicle needs to be capable of dealing with. And sampling in those areas where we expect that these situations are challenging, and showing then what is the performance that the vehicle shows as a good first estimate of safety performance. That does not only go for actually the safety solutions that we built in the vehicles. It's also looking to other types of safety solutions, for instance, things that you can change in the infrastructure and see how does then this influence the scenarios and how does this influence the behavior of other traffic participants. So some of the examples that we have up to very practical level.
And Olaf, adding to that, I think in our next webinar, we'll also talk about this because as Mikael said, the standards that are in place are very good guidance. But for example, ISO 26262 does not explicitly mention how to deal with scenarios. So how to do that, that is a topic that we will also discuss in the next webinar. And it's also explained in the position paper. So that might be worth reading that.
One final short question?
Yep.
Sure.
Yeah. With a short answer, the focus in this presentation is mainly on safety assessment of automated vehicles. Are we or others also working on the safety assessment of new road infrastructure, so the context the automated vehicles are operating in? Any opinion? Mikael?
Well, I would love for the road infrastructure to be perfectly predictable and perfectly consistent. That would make our lives much easier. In that dream world, we would all be really happy, but that's not going to happen. So I think it really is good to inform those designing roads, like what would actually be helpful. If you're not a sensor type of person, you might not have thought of what might help. But other than that, I think it's really a joint venture towards safety. It's yeah, failure has and will happen, and the best you can do is be on the lookout for signs or possibilities of failure and make sure you can handle those.
Yeah, and what comes to mind for me is the use of communication. Let's say making use of communication in automation. That's also where infrastructure can be very valuable and making life a little bit easier.
As long as it's perfectly consistent and doesn't have any glitches or downtime that we don't know of.
Yeah.
Yes, we have to stop.
Yeah, we have to stop.
We have to stop. It's 10 o'clock. I'm very
Yeah.
sorry. I know there are a lot more interesting questions in the chat. We will publish them, and we will also try to answer as many as possible, so they will show up in your Q&A after the session. We will also make sure that we share all the links so you can read the position paper, etc. So we make everything available for you. Thank you very much for your attention. Thank you very much to Henk, Olaf, and to Michael for today. And our next sessions you can find on the screen, and I hope to see you then. Goodbye.
Thank you. See you later.
Bye bye.
Bye bye.
See you then.